About me. So I've got 15 plus years of networking experience. I'm mostly into training and development field, guys. My key technical areas are multiple over here. So routing and switching, service provider, data center, security, design, wireless, cloud computing, and virtualization. I talk multi-vendor products. So Cisco is of course, my pioneer product. Apart from Cisco, I have got other uh, vendors as well, which I usually train and I am knowledgeable with. Certification wise, I have attended and attained a lot of certifications in my career. The list is over here. The premium ones are being CCI. I'm a VMware VCP. I'm a VMware VCI, which is a VMware certified instructor. Um, I'm also CCSI. I'm a Cisco certified system instructor. Plus, there are other uh, certifications which I've cleared. We'll talk about IP addressing and subnetting. Um, we'll also talk about VLSM. So this is one thing that is the primary focus. And then we'll talk about the network devices. What all are those? And how they behave. Uh, Similarly, we'll talk about how data communication happens using your IP address scheme. How does ARP happens? We'll discuss all those data communication expect at a very basic level. We'll see how two PCs or two devices sitting in a network, they can exchange the data. All right. So what we'll do is let's start with IP addressing and subnetting concept in the first half, and then we discuss the next thing later. So if I look into my slides over here, with respect to IPv4 addressing, we'll talk about what is an IPv4 address. How do you represent it? How do you write it? What is the relationship with binary and decimal number? Because when you learn IPv4 addressing stuff, you should know the binary addressing scheme, the conversion between binary to decimal, decimal to binary, a bit of maths involved into that, and we'll talk about the v4 address and subnet mask, how to calculate those stuff. Okay. Following this, we'll talk about the v4 subnetting stuff. So I'll use whiteboard to discuss v4 address and let's learn it. Okay. All right. So when you talk about IPv4 addresses, so so any device, when you talk about IPv4 address, first of all, we have got 5 classes, right? So this 5 classes, this IPv4 addressing concept was given to us by IEEE. So IEEE, manages the concept of IPv4 addressing and the regulations of it, right? So IEEE has given the concept of IPv4 addresses and the respective classes and how they will operate in your network. So we've got 5 classes over here. So the classes we represent like that. We have got class A, and every class has got a range of numbers. Okay, that range of numbers is between 0 to 256. Okay, so that is how it goes for class A. The range of numbers that has been defined is 0 to 127. For class B, the range of number that has been defined is 128 all the way to 191. For class C, the range of number is between 192 to 223. For class D, the range of number is between 224 to 239. And for class E, the range of number is between 240 to 255. So if you count from all the way from 0, it is till 255. So overall it is 256, right? So now what happens here is with respect to this, right? First of all, you should know before I talk about IPv4 address and discuss how to assign an IPv4 address and talk about the respective classes, etc., etc. First, we'll talk about a decimal to binary conversion. Okay, and then we'll talk about the opposite, which is a binary to decimal conversion. Right. So first, we talk about decimal to binary. In that regards, if I give you any decimal number, say I give you a number as 64, right? 64 being a decimal number. Now, if I need to convert that number into binary, right? So if I say that convert this 64 into binary representation. So normally what we do is, let me take out my pen. So what we usually do is we take this number 64 right? And then to get the respective binary, we actually divide this number with a factor of 2, right? So we take the value 2, so 2 divisible by 32, the carry or the remainder is 0. Then we take the factor 2 again, we divide it by 2, so it is 16, the remainder is 0. It is divisible, the value is 8, the remainder is 0. Divisible by 4, remainder is 0. Divisible by 2, remainder is again 0, and then it is divisible by 1, and the remainder is 0. Now you take the values from, these are your basically binary numbers, what you got, and you take it from your bottom to top. So it's 1 followed by 1, 2, 3, 4, 5, 6 zeros. So this means, the value 64 in decimal is equivalent to 1 followed by 1, 2, 3, 4, 5, 6. So overall, I've got 7 bits over here, right? Total is like 7 bits. Now, if I want to represent, this is giving me 7-bit number, right? So if I need to represent this into 8 bits, if I need to convert that into 8 bits, what I'll do is I will add a 0 in the prefix, all right? So to convert that into 8 bits, if I need to convert that into 8 bits, normally what I do is we write a 0 before this number. So 0 followed by 1 followed by 4, 5, 6, 6 zeros. So that overall, it is your 8-bit representation of the decimal number 64, right? Similarly, if you want to convert, any number, like for example, you take the value 128, right, as a decimal number, and if you need to convert that into a binary number, so it will be 1 followed by 7 zeros, 1, 2, 3, 4, 5, 6, 7. If you follow this method or the other way around, the same thing, will get this value. So here we are getting this into 8 bits itself, right? So any number you take, either you can approach this method, divide that number by a factor of 2, and whatever values you get, you take it from bottom to top, you get the respective binary of it. All right. Other way around is another simple technique I'll tell you. So what you write down is you write down the 8 bits. For example, let's say we have the 8 bits representation right from, let us say, right to left. So it is like 2 raised to 0, then 2 raised to 1, 2 raised to 2, 2 raised to 3, 4, 2 raised to 5, 2 raised to 6, and 2 raised to 7, right? So these are basically my 8-bit position values. Okay, so accordingly, if I get the respective answers, 2 raised to 7 is basically your 128, this is 64, this is 32, this is 16, this is 8, 4, 2, and anything to the power of 0 is 1. All right, these are basically your bit position values, right? So I've got 8 bits. These are my different 8-bit position values that I have. Now, for example, I got a number which is say 192. Okay, this is a decimal number, and let us say I want to convert that decimal number. This is my decimal number. I want to convert that into a binary, right? The question is, please convert that into binary. So you can do what? You can actually find out the combination of these values and find out which combination would give you the number 192. So always while doing this, go from your left towards your right. Okay, so 192 means if I add 128 and if I add this value 64 together, the answer is 192. So I can keep this bit position values as 1. Okay, and the remaining bit position values I can keep it as zeros, right? So this is giving me the value which is 192. All right, so the answer is 11 followed by 6 zeros. Okay, similarly, if I take a value, say example, 224, same thing. That's my decimal number. I want to convert that into the respective binary. So you know that if you add 128, 64, 32, if you add these 3 values together, you'll get the answer is 224. So it will be like 111 followed by 5 zeros. All right, so the answer is 111 followed by 5 zeros, 3, 4, 5. Okay, so I'll want to give you the exact values that you normally get. So the first value which is very, very commonly, used, that I'll say you. So the first value would be 128. Okay, next value in 8-bit position, I'm saying you 128. 128, the binary of 128 will be 1 followed by 1, 2, 3, 4, 5, 6, 7 zeros. Then we have got the value which is 192, right, which is double one followed by 6 zeros. The next value will be 224, which is triple one followed by 5 zeros. Next is your 240, which is 4 ones and 4 zeros. Next is your 248, which is 5 ones followed by 3 zeros. The next is your 252, which is basically 6 ones followed by 2 zeros. Next is your 254, which is basically 7 ones with a single zero. And the last value is 255, where all the bit values would be high. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and the value, if it is 0, for example, that means all the values would be 0, right? So basically the common combinations that we have, right? Or in the middle, if you want to have any combinations, for example, if you get a value like 48, right? So basically 32 plus 16 is 48. That means what will happen if the decimal number is 48, then you find out the combination, from right to left, go towards right to left and find out which combinations will give you the value 48. So 32 plus 16 is 48. So the rest everything would be 0. Only 32 and the 16-bit position would be high. The rest everything would be 0, right? So like that, I mean, you have to find it out. Okay. On the other way around, if I give you, the opposite, say I give you a binary number and then I tell you to convert that back into a decimal number, it is also a simple thing. So let me, write down that as well. So if I give you a binary number, let's say, so similarly, if I give you a binary number, so it is binary to decimal conversion, right? Very, very simple things. So if I give you a number like, for example, triple one followed by 5 zeros, 1, 2, 3, 4, 5, right? And if I ask you that what is the uh, equivalent decimal number for this binary, again you get the same logic. So you place the the decimal bit position values. So you place 128, 64, 32, 16, 8, 4, 2, 1, and you write down this binary on the respective bit position values. So it's triple one followed by 5 zeros. So we sum up the respective values for whose bit values are 1. So 128 plus 64 plus 32, when you add those three values, the answer is 224, right? So this gives you the value or the answer is 224. Right. Now, any combination that you get in your examples, for example, if I write down, I've got a value 10101010, right? Like that. A binary number is given to me. What is the respective decimal for that? This is binary. What's the decimal for that? So write down the bit position value as 10101010, right? So you get the answer as 128 plus 32 plus 8 plus 2, right? So this is 20. So 3, 5, 6, 7. So it is like 170. So the answer that you get is 170, right? So similar concept. So if you take out any binary number, just place that into the respective bit position values, and you add those values, which is on the higher side. Just add the high bit values, you get the respective decimal number. Okay. Now, there are other conversions also. I mean, binary to hexadecimal conversion, hex to binary, all those stuff. I mean, later down the line, when you go to CCNA, I mean, those conversions are important. But as of now, I mean, I'm okay with this, right? With the pre-CCNA level, if you know at least this, it is quite okay. Now, let me come back and talk about, the concept of, IPv4 addresses, that. Now, when you think about IPv4 addresses, let me write down that in a little bit down page. When you think about IPv4 address, I've told you that we have got 5 classes given to us by IEEE. The regulations are done by IEEE. Now, IPv4 address is divided into two part, right? So any v4 address that you take, it will have a network part and it will have a host part. Okay, so think like a very simple example over here, right? Think like a college or think like a school. Okay, I want to give you a quite a handy example so you understand, you can relate that, okay, with your real life. So think about let us say a college. All right, so we have got a building. This is a campus. This is a building. Now this building will have let us say just imagine I've got some three streams over here, right? We have got a stream of science, this is a stream of commerce, this is a stream of arts. Okay, now let us say I've got here 10 students in science, I've got 20 students in commerce and 30 students in arts. Those are the number of students that they are studying in this college with respect to this particular streams. Okay, so everybody will have their respective roll number, right? Everybody will have a unique ID card to represent in the college, right? So basically, for example, think about this 10 people, right? This 10 people will say, okay, my roll number is 1, my roll number is 2, my roll number is 3, my roll number is 4, like that up to 10. Same thing, these guys will say that we have roll numbers from 1, 2, 3, up to 20. They will say my roll numbers are from 1, 2, 3, which is up to 30. Right, but how do you actually differentiate them? Because their differentiation will be happening based on their streams what they have taken. So the first student from the science stream would have the ID card, or its identity will be like the student is from science team and his roll number is 1. Similarly, the student is from science team, his roll number is 2, right? His roll number is 3. So basically the stream name will come on the first and then the numbers would come on the second. So it's like commerce 1, 2, 3, then arts 1, 2, 3. So basically so you've got commerce followed by the numbers 1, 2, 3, whatever. You've got arts followed by the number which is 1, 2, 3, whatever, right? So same concept again, I can relate with another example. Let's say we've got a street. Say there is a street in UK, say it is Dallas, right? And say this particular street has got some 10 houses, right? Like that. So this is house number, say 100. This is house number 101. This is house number 201. Imagine that, right? So how do you represent that particular house with respect to this particular street, right? So with respect to this particular street, it is like there's a house which is 100. It is part of the Dallas street. So Dallas will come always on the first, followed by the house number. So it's like Dallas followed by 101, Dallas followed by 102, or say 201 in our example. Okay, so always, I mean, anything which is fixed, right? For example, the street is fixed. Okay, the number of house can be varying. For example, science, commerce, arts, the branches or the streams are fixed. The number of students sitting inside the branches, they could be variable numbers, right? Today I've got 10, tomorrow might be I've got some 25 students in science, right? So similar logic applies to the networking IP addressing concept as well. So if you think about that, I hope it is clear. If you think about that, so your v4 addresses will have a network part and a host part. So if I write down that in a box, okay, so this is your IPv4 address. Okay, it will have 2 part, network part and a host part. Okay, so now how do you actually write it down? So to understand network part and host part, you have to first consider the class of address, right? If you think about the class A address, the class A address rule, right? Rule. So basically what happens is your v4 addresses are normally the total size of the v4 address. If you can think, it is of 32 bits. Okay, the total size of the v4 address is of 32 bits. All right, So we have got 32 combinations of zeros and ones that can be spaced for a v4 address. Now these 32 bits are divided into two half, network half and the host half. All right. So think like network part is kind of a fixed. Think like it's a stream of signs or stream of or the street called as Delas, that is like fixed concept over here. And this is like the users or the nodes that will be part of the network. I can say the nodes that is part of this particular the fixed values. All right. So the v4 addresses are divided into 32 bits. Okay, logic. So if I think about the first address class, that is class A, the rule of class A is basically you have got 8 bits in the network part. Okay, and then we have got the 16 bits, sorry, 24 bits in the host part. Total is basically your 32 bits over here, right? 8 bits network, 24-bit host, giving you total combination of 32-bit address space. Now, what happens here is, for class A, the first, how do you represent it? We represent that into 4 octets. We represent the v4 address in 4 octets. They are separated by using a dot, separated by using a value called as dot. Okay, so I've got here 4 spaces where I separate these values with a dot. All right, so how do you write down an IPv4 address? So inside each, 4 spaces, total is 32 bits. So we have got 8 bits each. So each octet consists of 8 bits. So if I have a space of 8 bits, we know that we can have combination of 8 bits starting from all zeros. So all the 8 bits can be zeros, or all these 8 bits could be ones. So which means I can get a decimal number of either a 0 or till 255, right? Total, if I count from 0 to 255, it is 256 values. So 2 raised to 8, 2 power 8 is 256 values. So the range is basically between 0 to 255. So in every octet, you can write down this numbers, which is between 0 to 255. All right. In all the octets, you can write down these numbers from 0 to 255. Okay. Now, for class A condition, as I've told you, that the first 8 bits is your network part and the remaining 24 bits is your host part. That means this particular 8 bits that you see here, this 8 bits that you see here, the first 8 bit will be your network part, and the remaining 24 bits that you see here, they will be your host part. Okay, so now how do you represent the address? As I've told you, the class A address rule is this. This is how you represent it, okay, with 4 octets. So as per the range of class A is considered, we know the range starts from 0 all the way to 127. That's the range of your class A address. Now, how do you represent it? So if you want to represent this class A addresses, so that is the way you represent. So let me clear it out. So a class A, if you want to represent the address concept, so you start with, let us say, all the value as 0. Imagine, right? You have got 4 octets. On all the octet space, you write the value as 0. That means, this is your the first 8 bits. This is your next 24 bits. So just follow the first octet value. Okay, just follow the first octet value. What is the value it is? So the value is 0, right? So whatever value we have on the first octet, okay, that will determine which class of the address it is, right? So if it is a value 0, so we know class A address range is between 0 to 127. Okay, so if I have a value which is 0 in the first octet, that means this is following in class A range, right? That means this is my 8 bits, this is my network part, this is my host part. So basically, I can say that all the network bits are low or they are not used. Likewise, all the host bits are low or they are not used. This is kind of called as, though it is a class A address because the first value is 0 in the octet, that's fine. Though it is a class A address, but it is an invalid address. It is an invalid IPv4 address. I'll tell you why. The reason because none of the bits are in use, right? All the bits are 0. But this address in the world of networking has got a very, very special case, we call this address as a default route or a default address, okay, in the world of routing, the context of routing, and we'll see that down the line. Okay, but at a very, very basic level, I mean, if all the bits of the v4 address is entirely, not used, they're all zero, so it is an invalid IP address. So how do you start? So if you start like that, if you still say, okay, the first value is 000, okay, and the last value say it is 1, we're writing this in the decimal number itself, okay? So basically, we can say like that IPv4 addresses are represented in a dotted decimal notation, right? So this is basically another term. We call that I am representing this in a dotted decimal notation. So I write down decimal numbers, but they're separated by using a dot. Okay. Now, very simple here. Again, I can see this is the first value is 0, so it's a class A address. This is the network part. These are all my host part. So I can see that none of the network bits are used. From the host, at least one bit is used, right? So I've got a host, but without a network. Just like you've got a student, but without a stream. You've got a house without a street, right? So things is like, again, this is basically your invalid at IP address. So what you need at a very, very bare minimum is, you would need the IP address value should start with a value 1, right? So the first octet should have at least a value 1, and the rest, say if it is 0. So first of all, you see what is the value in the first octet, from which range it is. So it is from 0 to 127. So again, it's a class A address. So basically, this is the network part, the first 8 bits. This is your host part. So I can say that now there is a network bit which is in use, but all the host bits are 0, right? So there is a, network bit in use, but all the host is 0. Now this address is a very, very special address. Again, this is called as a network address of a network. Like think like, that science or commerce or arts, right? This is a network, right? So we've got a network here, we've got a, room over here, but there are no students inside that particular room, right? All the host values are 0, right? Now if I want to, accommodate the users in that network, so what we do is we keep this value fixed. We say one dot, and then we say 0 dot 0 dot, and we start assigning the users from your right to left. Okay, so the first value is 1 dot 0 dot 0 dot 1, right? That is your, valid IP address. This is called as a valid IP address, right? So we've got a network bit in use, we've got a host bit in use, that's fine. Now similarly, the second, or we can say this is your first valid IP address, right? Similarly, the second user will have 1 dot 0 dot 0 dot 2. The third user, the IP is 1 dot 0 dot 0 dot 3. And likewise, we'll continue. So we can go till this number, it will reach, the last number would be in a binary, right? If all the bits are high, with all these combinations, the last number can be 255, right? So far what we have is we have got, 255 users, right? Which is all, they're all part of this network address, right? They're all part of this network address. So think like a different way again. So this is a, let us say, classroom. The classroom address is 1 dot 0 dot 0 dot 0. We call that this is a network, this address of the network, and we have got the user sitting inside this particular classroom. So every user, has got the respective IP. So first IP, say it is 1.001. This is say 1001, this is say 1002, 1003, 1004, like that, right? So far you have accommodated, 255 users in that particular class or in that particular network. But still you have got, other host bits which is available, and we can use that, right? So it's a very, very big classroom. It's a very, very big network, right? In that very big network, you have got 24 bits in the host, right? That means you only have used a combination of the first octet, right? Still we have got 2 octet spaces where you can use. So exactly what I'm saying is, after this value, can I accommodate another user? The answer is yes, right? So after this value, what is the next value I'll get? Just write down here. So the next value is 1 dot 0 dot 1 dot 0, right? So we'll actually make the last octet, reset back to 0, and you will use the preceding octet or the third octet, make it to 1, right? This is also valid IP address. Normally I write VIP. and I read VIP, so it is called as a valid IP address. So from this combination, again, the next value is 1.0.1.1. The next value is 1.0.1.2, 1.0.1.3. Like that, we can continue till this last octet will go till 1.0.1.255, right? So we accommodated so many users, right? Still, we have got, the octet bits which can accommodate more number of users, right? So once I, finish the last octet, I can actually raise this value to the next value, and then we can use that combination. So after this, what is the next value that I have is again 1.0. I'll actually make this value to be the next one, which is the value 2, and reset the value on the last octet as 0. Now in this combination, I'll get 1.0.2.1, right, all the way to 1.0.2.255, right? So similarly, we can make it to 3, 4, 5, 6. So a time will come, when we'll actually get a particular value like this. Imagine you'll get 1.0.255.255, right? You will actually get this value. This is also a valid IP address, not a problem, right? So still you have got one octet where you can place more number of hosts. So after this, what is the next value that you get is 1 dot, you raise this value to 1, and you reset all those values to 0. This is another combination that you are getting, right? So after this, what is the next value? It's 1.1.0.1. So always you think like you are actually assigning the addresses from your right towards your left, okay? And whenever the octet values are becoming 255, the highest one, the preceding octet, you raise it to the next number, and then you follow that combination, right? So time will come, when you will see, a time will come when we will see this address, time will come when we'll see 1.255.255. 1 second. .255. A time will come when we'll see this particular value, right? Now this is a very, very special address that we have, okay? Where you see that we have got a network. This is a class A network, okay? Network bit is in use, but you can see that these are all your host bits. This is your network bit, right? This is your network bit. This is all your, host bit. You can see that all the host bits are basically high. So if all the host bits are high, this address is called as a broadcast address. This address is called as a broadcast address. Okay, so very, very common thing, right? If all the host bits are 0, like in this case, it is called as a network address. If all the host bits are high, the last value where all the host bits are high, it is called as a broadcast address. And in middle, whatever combinations you have, they are all called as your valid IP address. Okay, the meaning why it is called as valid IP address, because this IP addresses you can assign it to any device, any nodes, right? That is the reason it is called as a valid IP address, because you can assign this IP addresses to any nodes. All right. So what is the combinations you are getting here? Let me just clear it off. So you get the combination which is from, let me take a text. So the first combination that you have got is 1.0.0.0. This is basically your network address. Okay. After this, the first value which you got is 1.0.0.1. This was your, I can say, first valid IP address. And we have the combination. So I can go till last as 1.255.255.254, right? That is the last IP that I can go. So I can say this is the last, VIP address, right, of this network, right? And the last is 1.255.255.255, which is basically called as a broadcast address. Okay, so there is a term called as usable IP address, which means which IPs you can allocate to the devices. So usable IPs are all your valid IPs. All the valid IPs are basically called as your usable IP addresses. All right, so basically the range is between this. So whatever values you are seeing here, so all those values are basically called as a usable IP address. These values, right? They are basically your your usable IP address. Okay, so this address you can assign to the device, right? Now you can see that you've got 1.0.0.0, the first network, right? The first valid IP, the last valid IP. In the middle, we'll have all those combination values. We know that, right? And the last one is broadcast. So always remember, network address you cannot assign to any device. Any broadcast address you cannot assign to any device. Okay, only the valid IPs or the usable address of a particular network can be assignable to a device. All right. Now after this broadcast address, what is the next value that we get? After this broadcast address, the next value that we get is, of course, we'll actually reset all these values to 0, and we'll increment the first octet value to 2. The first value becomes 2, and the rest, all the values become 0, right? So it is, it is again a class A address because the first octet value determines the class of the address. So it is a class A address. And all the host bits are 0 over here, right? So this is, again, I can say this is your network address. I say NA as a network address. Then the first value would be 2.0.0.1, and the last value would be, with all this with all the possible combinations that we do, till the last value would be 2.255.2.255.254. There's the last value, and the last value of a particular network is a broadcast address where all the values are high. All right. So you can see that this is your usable IPs or the valid IPs. This is your broadcast address. This is your network address. So this is, let us say, now what we have is we have got two classrooms. Imagine, right? We've got two classrooms. This is your 1.0.0.0 network. This is your 2.0.0.0 network. From there, we have got these users are part of this network. We have got these users that are part of this network. Right now, what happens is by default, the users or the IP addresses which is part of the same network, they can communicate with each other. Okay, so all this usable IPs of the network 1.0.0.0, they can communicate with each other. All those usable IPs of the network 2.0.0.0, they can communicate with each other. But the users of, or the IPs of different networks by default, they cannot communicate with one another. Okay, so if I've got a user here having an IP from this range, if I've got a user here having an IP of 2.series range, they cannot talk to each other by default. Okay, remember that. So like this, what will happen, right? So let me clear it off. So like this, we are getting the possible combinations, right? So so say like this, we are getting the possible combinations of, so we've got from class A, we are talking about class A, addressing logic. So the first value was 0000. It was basically called as invalid IP address. Okay, next is 1.0.0.0, right, which is basically called as a network address. The next is 1.0.0.1 all the way to 1.255.5.254. This is basically your VIP. And the last is 1.255.255.255. This is basically your broadcast address of this network. We can also call this as a network broadcast. We can also call this address as a network broadcast, right? Now, what is the purpose of this broadcast address and all? We'll talk later. Okay, we'll see that. But remember, only very important thing is whenever you try to assign any IP address to a device, make sure it is called as a valid IP. You assign it from the valid IP range, right? Similarly, after this, what do you have? After this, let us say you have the next network. So next network is 2.0.0.0. This is your network address. We have got the range of VIP from 2001 to all the way to 2.255, 255, 254. This is basically your all the VIP from this network. And then 2.255, 255, 255. This is basically your broadcast address of this network. Okay, likewise, we'll go to the next network, which is 3.0.0.0, right? Again, the combinations will happen for 3 dot, 4 dot, right? 5 dot. Again, all those combinations will happen for each and every individual network, right? And we'll reach to the point. So for class A, the ranges, for class A, the ranges I've told you, For class A, the range that I've told you is, between 0 to 127, right? Sorry, 0 to 127. That is the entire range we have, right? So we started from 0, invalid. So this is the combination of one, series of 1, series of 2. Likewise, we'll have series of 3, 4, 5. So at the very end, I mean, we can go till the series which is 127.0.0.0, right? And basically, we'll have the numbers of 127 and the respective, values out of it. But the concept is this specific, 127 series that you see here, this 127 series is reserved for a special purpose, only from class A, reserved for loopback IP address. Loopback IP address for self-testing purpose. Okay, so normally we use this particular range of IP address as a loopback IP address, which is for your self-testing purpose, and we normally don't assign this IP addresses from this range to any of your user. Okay, so I can say the last value. So the last value, or the last, I can say, network of class A, or I should say like that, the last usable network, the last usable network of class A will be actually 126.0.0.0, right? So from that, you'll have the possible combination. The possible combination is 126.0.0.1 all the way to 126.255, 255, 254, and the broadcast address is 126.255, 255, 255, right? So that's your first usable network, that is 1.0.0.0. That's your last usable network of class A, that is 126.0.0.0. Right, and in the middle we have all the combinations of valid IPs, the broadcast address, etc. Remember, this loopback address 127, it is only from class A. Other classes, they don't have this concept of loopback addresses and all. So this address was only there, carved out from class A range. For self-testing purpose it is used. Okay, so we can assign the IP addresses from 1 dot till 126 dot for class A scope. I hope it is clear. So let me go back and talk about class B address scope now. Let me clear this off. Okay. Let me go and talk about class B addresses. So for class B, that we have, class B address range that we have. This is the range is between 128 all the way to 191. Okay. So we divide it into two halves. So we know that we have got the address range into two halves. So the half looks like that. So basically we'll have network portion and a host portion. So this is basically your 16 bits in the network, and we'll have 16 bits in the host. So that's your network part, and that's your host part. Okay. So what are the possible combinations that we get? So let me take a pen and write it down now. So the combination that we get is this. So the value that we start for class B, it is 128. That means my first two octet. Let me take a different one. So my first two octet that we have, my first two octet, and the last two octet has got a special meaning over here. This is my first two octet of 8 bits. This is the last two octets of 8 bits with respect to class B. So these values are in the network part. Okay, and these values will be in the host part. All right, and so I've got 16 bits host and 16 bits network, right? So which is the value that I start with? I start with the value 128 in the first octet. Rest every values will be 0. So when I see the value of the first octet as 128, I can easily understand that, okay, this is in the range of class B. Okay, so I should easily understand that, okay, since it's in the range of class B, the first two octets is in the network part and the last two octets are in the host part. Now you know that if all the host bits are 0, so here all the 16 bits that I have are having binary values of 0, right? If all the host bits are 0, So it is called as a network address. Okay. And what is the first valid IP from this network? It is 128.0.0.1, right? This is your valid IP. The next valid IP will be 128.0.0.2. The next valid IP is 128.0.0.3. Like that will continue up to 128.0.0.255. Correct? Not yet over, because we know that we have got 2 octets in the host, so we can actually go and use the third octet value as well for the host part, right? So after this value, the next valid IP that we have, it is 128.0.1.0. Same condition, same logic it will apply, right? This is also valid IP. Likewise, we'll have combination of this series, right? 1.1, 1.2, 1.3, like that. Then we'll increment to 2.3.4. So time will come, when I'll have a value which is 128.0.255.254. Correct? So this is, I can say, this is the last valid IP from this network, right? From 128.0.0.0 network. So from this network, this is the last valid IP. Okay. And what is the broadcast address? If all the host bits are high, that is called as a broadcast address. That means the value would be 128.0.255.255. This will be called as a network broadcast of this network. That's your broadcast address. All right. So what is the usable IP that we have got? So I've got a usable IP, which is, let me take a text over here and write it down. So basically I've got, the first value was 128.0.0.0. This is basically my network address. And then I've got 128.0.0.1 all the way to 128.0.255.254. They are my usable IP, or the valid IPs that I can assign to a host or to a node. And then my broadcast address is 128.0.255.255. This is basically your broadcast address. All right. So the first value, network address, the last value, broadcast address, can't be assigned. In the middle, they're all my usable address. They can be assigned to the individual nodes. All right. So after the broadcast address, normally what we do, the next value that we get is a new network, right? So after this particular broadcast address, the immediate next value, whatever we get, there is a new network address. So let me write down that as well. So after this address exactly, so if I after this address exactly, I'll be getting a new address, which is basically, let me write down here itself, 128 dot, the next value will be 1, and I'll reset back to 0 and 0. This is basically a new network, because you can see the values are changing. This is your first 2 octets, values are 128.0, and the value over here, it is 128.1. So I've got a different value in the network part. So it's a new network for me. And from this, I'll have a combination of the host values. So if the host bits are all 0, this is my network address. If the host bits are all 1s, that will be my broadcast address, right? And then in the middle, I'll have all the combinations of valid IPs. So for this, what is the answer that I get? Let me just clear it and write it down. For this value, the answer that I get, that is, the next is 128.1.0.0, right? This is your network address. So the usable IPs are 128.1.0.1 all the way to 128.1.255.254. They are my valid IPs or usable IPs, and 128.1.255.255. This is basically your broadcast address. Okay. Similarly, the next network address is basically what? 128.2.0.0, right? That is again same logic. Network address 128.2.0.1 all the way to 128.2.255.254. They are all your valid IP. and 128.2.255.255. This is your broadcast address. All right. So the idea is, network address. In the middle, we have got all the valid IPs. The last is broadcast address. After the broadcast address, the next value, whatever we get, it's a new network. Okay. So like this, you understand that I'll have, this, the second octet of class B will go till 255, and then I can increment this value to, the next number, that is 129, right? As we know, the range is between 128 to 191, right? So I'll have a bit more lot of networks over here, right? So like that, with all the possible combinations, I can say the last network address of class B will be your 191.255.0.0, right? That will be the last network address of your class B. Okay. If somebody asks you that, what is the last valid IP of class B? So the answer would be 191.255.255.254, right? That is the last valid IP of your class B. All right. So I hope it is very much clear to everybody. The next concept, obviously, what we have is for class C. You've done with class A, you know what is the concept behind the scene. Then we have class B. Just now you've seen how it is done. Now we have got class C, right? Let's talk about that. So regarding, class C. Class C address range is one of the simplest address that I like about, or address block that I like about. The address range is between, 192 to 223. All right. And again, the same logic, if you think about the network and the host part, so you have got the division like that. You have got 24 bits in the network part, and you have got 8 bits in the host part, right? That's your network part, and that's your host part. All right. So very simple. So the range starts from 192. So if you write down the, the address blocks in a proper way. So how do you write it down is, you have got 4 octets over here. And this is your 8 bits, all are 8 bits, right? So the first 3 values, or the first 3 octets, are your network part, and the last octet is basically your host part. Okay, that's the logic. So the starting value of class C is 192.0.0.0. So the first 3 octets are basically your network. The last one is your host. So you know that if all the host bits are 0, if the host value is 0, so it is called as a network address. Okay, so the first valid IP would be 192.0.0.1. That's your first valid IP. Now all the way to 192.0.0.254. Okay, that's your last valid IP. And if you make the host bit as all high, so 192.0.0.255, right? If all the host bits are all high, the answer is 255. So it is your broadcast address. Right? That's your broadcast address of this network. So after the broadcast address, as we all know, is what we'll get is a new network address. So after this, the next value that we have, it is 192.0. We'll increment the value as 1 and reset back to 0. So that is your next network address. This is the network part, that's the host part. This is your next network address. And same logic, we have the values from .1 all the way to .254 as the VIP. The last value .255 is your broadcast. Okay, and after this, the next value, whatever we get, it is 192.0.2.0. That's your next network address. So likewise, the combination follows, right? So a time will come when I'll get, the answer is 192 dot, 0 dot 255 dot, 0. That's fine. This is a class C address. This is the network part. This is the host part. So it is a network address concept, right? So if anybody asks that what is the last network address of class C, it's very simple. So the answer is 192.255.255.0. That's the last network address of your class C. The answer is not yet correct because this value has to be what? This value has to be 223, right? So 223.255.255.0. This is exactly the last, network address of class C. Okay, and you guys got the logic, how to represent a class C IP address. So with this logic, let me again write it down for you guys. So let's say the class C range is 192 to 223, and the address starts like that, 192.0.0.0. That's your network address. 192.0.0.1 all the way to 192.0.0.254. That's your VIP address. 192.0.0.255. That's your broadcast address. Okay. And after the broadcast address, what you get is the next new network address. So the next network address is 192.0.1.0. This is your again network address. Same logic applies, 192.0.1.1 all the way to 0.1.254. That's your VIP, and 192.0.1.255. That's your broadcast. Right. After that, you have got the next network, which is 192.0.2.0. That's your next network address. Like that, you will get 192.0.3.0, 4.0, 5.0. So possible combinations will happen with all those values. So the last network address, if I can think, so might be this is the concept that you get. The last network address of class C is 223.255.255.0. If you say last valid IP of class C, this will be 223.255.255.254, right? That is how it is for class C. Next that we have is basically class D or class E stuff, right? So class D, class E, they're for specific purpose. So if you think about, a class D address range, the address range is basically between 224 to, 224 to 239. So basically class D is used for multicasting purpose. So class A, class B, and class C, they are going to provide us unicast IP address. Okay, by using class ABC address, normally we can go with, one-to-one communication. So they'll provide unicast IP address. So basically what I mean is all the valid IPs, you can write down like that, all the valid IPs, all the valid IP address gives us unicast communication from class ABC. Okay, and you can say that, from class ABC, the network broadcast addresses that we have from every network, the network broadcast address that we have are used for broadcast communication. Okay, I'll show that how it works. Very simple thing. So whatever broadcast addresses you are getting from every networks, they are used for broadcast communication. But whatever valid IPs we have, they are all used for unicast communication. Right. Now, with respect to class D that I've told you, so any IP that we have from class D from that range 224 onwards to 239. So class D addresses are used for multicasting purpose. Multicasting is basically for one to group communication, one-to-many communication, right? So generally in this network fundamental level, we'll not talk about multicasting. We'll not talk about, multicast routing. This is taught basically in CCNP level. Okay. But at the end of the day, I mean, you need to understand that we'll work, we'll assign, the IP addresses from class A, B, C to my nodes. Okay. So whatever, if you get a value like, 224 to 239, so any addresses, if you think like it is starting like that, so it is say 224 dot, whatever number. When I say XXX, so it's whatever number, all the way to 239 dot whatever number. So those numbers are basically meant for class D addresses, and using that number, you can do multicasting in your networking, right? So it is possible to do a one-to group communication, or to do a multicast based communication with this IP address. And that is out of the scope from this level of knowledge. So we'll not focus on class D addresses over here. Okay. And the last address that we have, it is in the range, it is class E. So class E is basically the ranges between 240 to 255. Now, the purpose of class E is used, or I can say is reserved for research and development purpose, right? For R&D purpose. So basically, whatever IPs you have from 240 all the way to 255, they are called as class C IPs. They're used for R&D purpose. Now, if you want to use a class C address range for your organization, I mean, there is a huge procedure that you need to follow. So you need to first request your ISP. ISP will send a request to, INA, IEEE. Their team will come and physically verify that, what R&D your devices has to perform on the network, and based on that, they will verify. And if it is found legitimate, then only the class C addresses can be given. Okay, so generally saying, class C addresses are for R&D, class D are for multicasting. We will be using class A, B, C, regularly in our day-to-day environment for your IP addressing logic. All right. We will go and talk about, subnet mask right now. So let's talk about, along with IP address, the most important thing that we have to assign along with IP is also your subnet mask. Okay, let me talk about that as well. So the next thing that we have is basically called as subnet mask, right? So if you think about any class A address, any class A IP, for example, I'm just giving simple examples, 10.1.1.1, right? You know what? With every class A address, you get something called as a subnet mask. I mean, every class of IP, you need to write something called a subnet mask, right? So I'll just give you the value what you normally write. The mask is 255.0.0.0 for class A, right? So if it is, let us say class B IP, if it is a class B IP, for example, class B IP has got, say, 172.16.1.1. That is a class B address. What is the corresponding, subnet mask for it? Subnet mask for this address would be 255.255.00. If I take any example of class C address, for example, 192.168.1.1, the corresponding subnet mask for this will be 255.255.255.0. Now, what the subnet mask is actually representing? It is representing which bits in the IPv4 address are your network part, which bits are in the host part. So, for example, if you think about, let us say this number 10.1.1.1, and I write down the mask as 255.0.0.0. So always remember that along with IP, you have to mention the subnet mask of that particular IP address. Okay, so IP goes alongside with subnet mask always. So what does this mask represent? So you can see that all the 8 bits in the mask is all high, and the remaining 24 bits are all low. That means the first corresponding octet of your IPv4 address, it is the network part, and the remaining 24 bits corresponding bits in the v4 address is your host part. Okay, so subnet mask always represent that what are the corresponding bits in the IPv4 address, out of which bits are network part and how many bits are there in the host part. Okay, so similarly, when you have write down 172.16.1.1, you see that the default mask, we call this as a default subnet mask. right? Default subnet mask of class A, B, C respectively. So this mask is representing, the first 2 octet is there in the network part, okay, and the remaining 2 octets are there in the host part. So high represent network bits, low represents your host bit. So here the first 3 octet is your network part, and the last octet is your host part. All right. Now, along with subnet mask, what you get is another concept, very similar concept with mask is your CIDR, right? CIDR value. So CIDR stands for, let me write it down. CIDR stands for classless inter-domain routing. Okay, it's a value. So for example, if I write down any class A address, so for a class A address, any IP address that you get from class A, the mask is 255.0.0.0, okay, and the corresponding CIDR value would be /8, okay. For any class B address that you write, the mask is 255.255.0.0, and the corresponding CIDR value would be /16. Likewise, for any class C address, the mask is 255.255.255.0, and the corresponding CIDR would be /24. Okay. So if I write any class A, class B, C, I'll have a respective CIDR. So for example, let's say that I wrote a value, 10.1.1.1. Okay. What is the mask? We know that the default mask is 255.0.0.0 of this particular IP. So what is or the other way I can write it down is like, hey, 10.1.1.1 has got a CIDR value of /8. So if you have a CIDR, /8 means the first 8 bits are in the network part, and based on the CIDR, you can find out the mask. So if first 8 bits are in the network part, that means, the mask is R255.0.0.0. The first 8 bits are high, right? Similarly, if you write down 172.16.1.1, the CIDR is /16. It's a class B IP. So 16 bits are there in the network part. So the first 2 octets will be high in the subnet mask, and next it is all zeros. Likewise, you take 192.168, 1.1 as an IP of class C. The CIDR is /24. That means the first, 3 octets are there as the subnet mask or as high in the mask. All right. So we can say like that these are the default CIDR of class ABC. These are the default subnet mask of class ABC. All right. And the mask normally represented along with IP address always. And the subnet masks are always going to represent that for the corresponding IP, how many bits are there in the network part and how many bits are there in the host part. So high values in the mask represent your network bits, low values in the mask represent your host bits. All right. All right. So the next topic that I want to talk about is, how data communication happens using IP addresses, using IP address and MAC address, both. Because we're talking about, the network, which is Ethernet, right? So Ethernet based networks, when you think about, we would need 2 addresses always, which is IP and MAC, and based on that, your communication would happen. So let's say that I have, 2 devices. So this is my PCA, and I've got another PC over here. Say I've taken a proper Ethernet cable type to connect it with the proper format. So imagine this is my PCA. This is PCB. Now, the very first thing that you need to think is, you have to go to the network adapters of both these PCs and assign a respective IP address, right? So they want to exchange some type of data between them, right? whatever type of data that they want to exchange. Your data can be of, multiple types. Very simple it is. We can have a clear text data, or we can have voice-based data, or we can have, video-based data, right? So whatever data that we are going to send, either clear text, voice, or video between these two PCs, what we need at a bare minimum is an IP address, right? So we have to go and assign this particular PC's, say, an IP address. Say we assign an IP address from class A. I say 10.1.1.1, and accordingly the mask could be 255.0.0.0. So I have to go to the network adapter of PC A and assign an IP address and a subnet mask. Similarly, I have to go to the adapter of PC B and assign an IP address of, let us say, from the same network. I'm giving the second IP as 10.1.1.2, and I'm giving the mask of 255.0.0.0. So once I do that, you know that every network adapter, what we have over here, so we are assigning the IP address to the NIC of both these PCs, right? So this NIC will have, a physical address, a MAC address. So imagine that, this PC has got a MAC address, which is, normally it will be in, 48 bits, but I'll just write the first 4 values over here. So let's say it is like that. So what, quadruple A, all are quadruple A as the MAC address. Okay. Similarly, the MAC of this particular PC, say it is quadruple B. This is how the MAC address will look like. Sometimes it is separated by dot, or sometimes it is done using a hyphen. All right. Now, the moment you assign an IP address and a mask, so basically the MAC address is called as a physical address, the IPs and the mask are called as a logical address. So moment you assign an IP address and a mask to a particular PC, okay, the very first thing what the PC would do is, let me write it down for you guys. You assign an IP address and a mask to this PC, assign IP and mask to this PC. The moment you assign an IP address and a mask to any device, not only a PC, but any device, you assign an IP address and a mask, that device, it performs one operation called as binary ending. It's a very, very important operation. It does an operation called as binary ending. What does it mean is, it will the PC automatically would convert this IP address values into binary and the mask values into binary, and in case of engineering logic is multiplication, right? And means multiplication. So we'll take out the binary of 10. So binary of 10 is basically 1010. So it is like 8421. So it is the first 4 bits are 0. Then it is 1010, and the binary of ones, all the 7 bits will be 0 and followed by the last bit as 1. So likewise, this is the binary representation of my IP address 10.1.1.1, right? And the mask of 255.0.0.0, it means all my 8 bits in the first octet is high, followed by all the bits here it is 0, all the bits here it is 0, and all the bits here it is 0. So ending means it's multiplication. So what will happen is you will get the result now. So the result is basically right, 1 multiplied by 0 is all 0 and followed by 1010. Anything multiplied by 0 will be 0 itself. So this is all 0 in 8 bits. This is again all 0 in 8 bits. This is again all 0 in 8 bits. So the answer is, when you convert it back to your decimal number, so each octet value, when you convert it back to your decimal number, you get the answer as 10.0.0.0, right? So get the logic what you got. So you have assigned an IP address and a mask to a PC. The PC automatically does, or any device, not only a PC, any device, when you assign a IP address and a mask value, the device would do binary ending. Okay, so it will convert the binary of, the corresponding decimal numbers into binary of IP and mask and multiply the value, and it will get an answer. This answer is basically what it got is a network address. The result that you get after doing binary ending, it is basically a network address. So the PC understands that, okay, based on this IP and the mask combination, my network address for this is 10.0.0.0. So this IP and this mask belongs to this network. And based on this, mask value, that means the first octet is in the network part and the remaining octets are in the host part, right? So it knows that, the first octet, this value is in the network part and the next is the host part. So the PC automatically knows using binary ending two important things. The first important thing it knows is to which network address, this PC is belonging. It says that, okay, I belong to this network 10.0.0.0, and automatically you can also say it is, in /8, right? And the PC automatically will understand that, what are the VIP range of this network. So with which IP address it can communicate, right? From this network, what are the VIP range that we have? So the VIP range is between 10.0.0.1, right, all the way to 10.255, 255, 254, right? And also it knows that, 254. And also it knows that the last IP is the broadcast, right? It knows that. So basically, by using binary ending, the PC is understanding to which network address it belongs, what are the VIP addresses it has. That means this PC knows that, any IP from this range on the remote side, the PC can be able to communicate with. So on the remote end, if I have a PCB and the PCB is having an IP address, which is anything from this IP scope, this IP range, this PC can send some traffic to them or receive some traffic from them. Data communication can happen, right? Same logic over here as well. When you go to PCB, you assign the IP address and the mask to it, does binary ending, and same logic, right? So it will also, get to know that, okay, my network address is gonna be 10.0.0.0/8, and again, my valid IP address is in the same scope itself, right? So it knows, they can communicate with each other, right? So at the end of the day, this is the very first thing that will happen, right? Now, as an administrator, right? Um, as a network administrator, we normally do what? We normally use a command called as ping to test my, IP connectivity, to test your IP connectivity. So this is very important. So if you actually, as an administrator, if you go to a device and you ping some other, remote device, and you check the IP connectivity between those devices are happening, that means you get rest assured, that your basic communication from point A to point B or between those two devices can happen, right? If your IP connectivity is there, means your data communication can happen, right? So if you go with the logic of OSI model, right? So you've got, the application layer, which generates your data. That data will normally come and talk to your, transport layer at layer 4. The layer 4 will normally talk to your, layer 3, the IP layer. So between source and the destination, if you have the layer 3 connectivity, right, which is happening at the end of the day, that means if you can test layer 3 connectivity, that means layer 3, layer 2, and layer 1, right? So if all are possible, then only your layer 3 connectivity will be possible, right? So once you send a traffic, say a ping traffic, right? So ping is basically a command. It will generate an ICMP packet. So when you give a command called as ping, it generates a traffic called as an ICMP traffic to test the connectivity between the source to the destination, right? On the process, what happens is, so ICMP is part of your, layer 3. On the process, what happens is you will check the layer 2 also and layer 1 also, right? So if your layer 3 communication is possible between the source and the destination, that means your layer 2 and layer 1 is also happening. That means whatever data you receive from the upper layer at layer 3, the data can be delivered from point A to point B, right? So as an administrator, if you send a traffic using ping and you test the connectivity is available, that means you rest assured that your data communication can happen, right? So this is one thing. The second thing that I want to talk about is a very, very important concept is, what happens when you go and do ping, right? What happens when you go and do ping? Okay, let's understand that. So I go to PCA, I go to the command prompt of PCA, all right? And on the command prompt, I said, ping the remote IP, which is say 10.1.1.2. Once I do that, what happens is, so ping is basically a command. It will generate traffic called as ICMP traffic. So ICMP is a protocol which serves the job of ping. ICMP stands for Internet Control Messaging Protocol. All right. So now what will happen is you will have right now an ICMP header which will be generated because of this command ping that you gave. The ICMP header would be generated at layer 3, right? And this ICMP header will be at layer 3, right? And then we will have the layer 2 header, which is basically the Ethernet header, which is at layer 2, will be encapsulated with your ICMP header, and then the traffic will go along the media to the destination. That is the first logic you need to understand, right? When you think about the ICMP header, there are multiple, entities present inside the ICMP header. So most of the important entities that I'll take right now, it is, the source IP and the destination IP of your packet. Okay, there are other entities also, which I will discuss later down the course. But at a very, very basic level, I mean, which information you have in the ICMP header will take that, right? So basically, this will be an echo request. We normally say that when you ping somebody, when you send ping and try to test connectivity with your remote peer, we normally say that we are sending, echo request. So we are generating an ICMP header, which is type called as echo request. Okay. We will be expecting echo reply from the remote peer. We expect that we would be getting something called as an echo reply from the remote peer, right? For my echo request, I'm going to expect that I'll get an echo reply from my remote peer. Then only I'll consider my ping is successful. So if I send you an echo request, if I don't get an echo reply, apart from that, if I get something else like request timed out, source quench, destination host unreachable, etc. So any other different messages makes me understand that my destination is not reachable. My remote peer is not reachable. All right. So very simple thing. So I'll generate an ICMP header, which is of type an echo request. Okay. So this ICMP header, so basically my echo request would be generated. Okay. And then you will add the source IP. All right. You will add the source IP of your packet. You will add the destination IP of your packet. Okay. So source IP is basically your own IP address, which is basically your 10.1.1.1. That's your source IP. Destination IP is basically the remote peer to which you are trying to send the ping traffic to. That will be your 10.1.1.2. Okay, that is a remote peer. Right now, this is your layer 3 information. So at layer 3, you know that you're sending an ICMP echo request. That's your source IP. That's your destination IP. Right now, you know that as per data communication happens. So whatever data you generate at layer 3, it will go to layer 2. At layer 2, you will add your layer 2 headers. So layer 2, you will add basically your Ethernet header. So in Ethernet header, you have got the concept of MAC address. So basically, you will add along with layer 3, you will add layer 2 header as well. So layer 2 header would be basically your source MAC, right? Source MAC and destination MAC. Okay. So source MAC is basically the PCA MAC address, which is quadruple A, starts with quadruple A, as you've seen. And the destination MAC is right now not known. So if you look into this particular computer, this computer will maintain something called as a local ARP cache. I'll talk about ARP right now. So it is called as Address Resolution Protocol cache, local ARP cache. So it will maintain, the IP and the MAC, resolution values inside the cache. So inside this particular PC, it knows that it has got a local IP, which is 10.1.1.1, and this MAC address is quadruple A. He knows that binding, but he does not know anything apart from that. Similarly, PCB also has got a local ARP cache. In the local ARP cache, he knows that his IP address is 10.1.1.2, and his MAC address is, quadruple B. Right? So the PC knows that, but apart from that, anything else is not known to the PCs yet. So now what will happen is when you send a ping traffic to somebody, you know the source IP and the destination IP, right? You know your IP, you know to which IP you're trying to ping. That's fine. And the source MAC is locally, like your MAC, you resolute that from the, you found out that from the local ARP cache, right? That 10.1.1 has got a source MAC of quadruple A, but you don't know what is the destination MAC address of 10.1.1.2. Right? If you do not know what is the destination MAC of 10.1.1.2, what we'll do is you will try to find out that, okay, if I need to reach 10.1.1.2, what is the MAC address of that guy? Now to find out that, you will actually send something called as an ARP request, right? We normally call that as an address resolution protocol request, ARP request. So this PC will generate an ARP request. Okay, so ARP request basically will go like that. So think like very basic thing, ARP request is like, who is, let me just write down here, having some issue. Like, who is, one second. Let me take a text. So your ARP request will follow like that. I mean, what is the MAC of, what is the MAC of 10.1.1.2, right? So basically you are asking with the ARP requests, and you are trying to resolve that what is the MAC address of this IP address 10.1.1.2, and the request normally will go as a broadcast, right? The request will normally be delivered as a broadcast. Now how it happens, let me tell you here. So right now what will happen is you are going to send an ARP request. So your ARP request packet will look like that. So the ARP request packet will have a source IP, which is basically, source IP is basically your 10.1.1.1, right? You are sending an ARP request for a destination IP. The destination IP is 10.1.1.2, right? You will have a source MAC. The source MAC address is yourself, quadruple A, right? And the destination MAC basically is, a broadcast. So represent broadcast like, all FFFFF. So broadcast MAC is like that, right? All FFF in 48 bits. This is how your ARP request normally looks like, in your, a packet structure format, right? So you're sending an ARP request from your source IP to a destination IP. Your source MAC is yourself for the destination MAC. If it is all F in 48 bits, it means it is we call that as a layer 2 broadcast, right? It is called as a layer 2 broadcast. So now what happens is this ARP request goes over the media to the PCB. PCB says, oh, I'm getting an ARP request. I see that the sender MAC address is, quadruple A. The destination MAC is broadcast. So broadcast means anybody can process this particular, frame at layer 2. Then when it checks for layer 3, it will find that the destination IP is 10.1.1.2, right? So 10.1.1.2 means the ARP request was made for this PC because he's having this IP of 10.1.1.2. Then he will give an ARP reply. Before he gives an ARP reply, he will actually cache its local, ARP, cache table. He'll say, okay, 10.1.1.1, I'm getting an ARP request from 10.1.1.1. So, I know that you are part of this MAC address. So let me write down in my cache, and then I'll give you a reply with my, info, like with my MAC info, right? So it will say that with an ARP reply, it will say, one second. Generate an ARP reply now, and the source IP would be, your 10.1.1.2. The destination IP would be your 10.1.1.1. Okay, the source MAC is basically the MAC address of this PCB. And the destination MAC will be basically your quadruple A, right? So always remember, ARP request is a layer 2 broadcast, and ARP reply is a unicast, right? So ARP request is a layer 2 broadcast, and ARP reply is always a unicast. So you can see that, the reply is happening to a particular, entity. So now your PCB will give a reply to PCA, and because of which PCA will now develop its local ARP cache and find out that, okay, 10.1.1.2 has got this MAC address of quadruple B. Okay, so now you remembered that, when you were trying to ping, your destination MAC was not known, because of which the PC has done an ARP request, found out the MAC address of 10.1.1.2, and now this MAC address would be written over here, right? So the MAC address would be now quadruple B, right? So now your ping packet, your ICMP packet will travel from point A to point B. Okay, so you're sending an ICMP echo request from PC A to PC B, but over the process, try to understand that you have to know the MAC address. To know the MAC address, you can do an ARP request, get an ARP reply, find out the MAC, build up your local ARP cache, and then only it is possible. So once you send the ping means you're sending an echo request, right? So PCB is getting this particular echo request packets. PCB is finding that, okay, the destination MAC is me, quadruple B, the destination IP is me, 10112. All right, and let me generate an echo reply to 10111. Okay, so for echo reply, how it will happen is, if you write down here, for echo reply, this is my echo reply packet. On the right side, I'm writing my source IP of the echo reply is basically 10.1.1.2. My destination IP is 10.1.1.1. My source MAC I already know it is quadruple B, and my destination MAC it is. So I have my local ARP cache now. So I know that to reach 10111, I know that the MAC address is quadruple A. So I generate an ICMP echo reply, and this echo reply can go from PCB to PCA, and your ping will be successful. All right. So at a very, very basic level, I mean, I hope it is clear. I mean, you understand that what will happen if I give an IP address to a device, what is binary ending is all about. If I have to communicate between two PCs sitting inside the same network, right? So I can see that 10.1.1/8, 10.1.1.2/8, they're part of the same network, how the communication happens. So if I do not know the MAC address of my destination, I have to do an ARP, find out the MAC, and build my local ARP cache on both the PCs, and then only my communication can start. Let's talk simple. I've got two PC here. This is your PCA and PCB. They're plugged via a proper Ethernet media. You give an IP address here, 10.1.1.1, having a default mask. Give an IP here as 10.1.1.2, having a default mask. This PC is having a MAC address, which is quadruple A in 48 bits, let's say, as an example I'm giving. This PC's the MAC address is quadruple B. First thing first, when you assign an IP address and a mask, I mean, the PC will do binary ending, and the PC will know that to which network address it belongs. It belongs to 10.0.0.0/8 network address, and it knows that what are the VIP scope it has, so it can communicate to 10.0.0.1 all the way to 10.255, right? It knows that. Same thing, this PC also knows that, okay, I belong to 10.0.0.8, and this is the VIP address that I can communicate with. Okay, now these PCs will have by default something called as local ARP cache. Where it will write down the binding of your IP2 MAC. So it will say that, okay, my IP is 10.1.1.1, and the MAC address is quadruple A, whatever we have. Same thing, this guy will also have its local ARP cache, and this is 10.1.1.2, and the MAC address is quadruple B. Okay, now what is the concept? Very simple. So I want to ping and test the connectivity between PC A to PC B, or vice versa, whatever. So when you say the command ping space some destination IP, okay, basically you are introducing a protocol to work for the command ping. The protocol is ICMP. This ICMP protocol, it sits at layer 3 of your OSI model or TCP/IP model, however you say, right? So for ICMP, when you give a command ping, what you're doing is you're generating ICMP echo request packet. You're generating an ICMP echo request packet. Okay, so this echo request packet would be added with source IP. The source IP of the packet would be what? 10.1.1.1, right? The packet would have a destination IP. Where you're trying to ping is 10.1.1.2, that is the destination IP. And at layer 2, this is all your layer 3 information. So you know that with respect to OSI, the packet will move down to layer 2 and it will add the layer 2 header. So basically we'll add, the source MAC and the destination MAC at layer 2. The source MAC will be basically your quadruple A, right? And the destination MAC is basically unknown, as simple as that. So generating an ICMP echo request packet, you're trying to ping, but your destination MAC is unknown. So if your destination MAC is unknown, your packet cannot move to layer 1 because your layer 2, the packet is, you have not added the MAC address, right? So your packet encapsulation is failing because destination MAC you have not added, so packet will never be moved down the layer, right? So you have to know the MAC address, and then only you can send the traffic to the physical wire. So for that, what the PC will do is it will generate, since the MAC address is unknown, the PC will generate an ARP request, address resolution protocol request, to find what is the MAC of 10.1.1.2. Your ARP request would look like that. So ARP request will say my source IP is basically 10.1.1.1. My destination IP is 1 second, 10.1.1.2. My source MAC is quadruple A, and my destination MAC is basically a layer 2 broadcast, because I do not know to which MAC address I should send the traffic, right? So basically I'm generating the traffic as a layer 2 broadcast. So this ARP request will travel from PC A to PC B, right? So PC B will receive the ARP request and will say that, okay, I'm seeing the ARP request. The layer 2 is a broadcast, means anybody can process it. When the PC looks for at layer 3, the PC finds his IP address over here, which is 10.1.1.2. So he knows that the ARP request was made for him, and then it will do what? It will give ARP response. So now the PCB will generate an ARP response. Before that, he got the ARP request, right? So that ARP request, because of the ARP request, the PC will know that, okay, 10.1.1 has got a MAC address of quadruple A, and that MAC address he will write it down in the local ARP cache. And then he will give a ARP response. In the ARP response, he will write down, in the ARP response packet, he will write down that, okay, source IP is 10.1.1.2, that's me. Destination IP is 10.1.1.1. Source MAC is myself, okay, and the destination MAC will be unicast, which is that quadruple A guy, right? So always remember, the ARP request is a broadcast, layer 2 broadcast, and the ARP response is a layer 2 unicast. Okay, so you get an ARP response. When you get an ARP response, what happens here? Your PCA says that, oh, I know that this MAC address for 10.1.1.2 is quadruple B, right? Now remember, your destination MAC was unknown here. So now what will happen is this PC will now, get to know what is the destination MAC, and the destination MAC will be filled up with the, MAC address of quadruple B, and then this ICMP request can be sent to PCB. Once PCB receives the ICMP request, he will do what? He will check that the ICMP request was made for its own MAC address, the destination IP is matching with his own IP, then he will generate an ICMP echo reply, right? So this PC will now generate an ICMP echo reply, right? So this packet would look like, the source IP would be 10.1.1.2, destination IP would be 10.1.1.1. At layer 2, the source MAC address would be quadruple B, and the destination MAC address would be quadruple A. Now, how does it know the MAC addresses? Very simple. It knows the MAC address from the local ARP cache. It knows that, okay, my MAC address is quadruple B. My remote where I'm trying to give a reply, his MAC address is quadruple A. Now the ICMP echo reply will go from B to A, and A will receive the ICMP echo reply, which means the ping is successful. Very simple. So now let us say if I need to communicate between two devices which is not in the same network, then I would need something called as routing. As simple as that. So if let us say I've got here you know um, something which is say different IP here. So say not this IP, right? So I've got a different IP say over here. Imagine I've got say 20.1.1. 2 over here, imagine. And this is the mask which I have. So in this scene, what is happening is this network is different, right? So this network is 20 dot, 0.0.0/8. So even its conditions are different. So this is 10 dot series network, that is 20 dot series network. So your communication would by default not happen between two separate networks. Okay. So in that case, if I need to communicate between two separate networks, I need the concept of routing. Now let's use one tool called as a Cisco packet tracer just to demonstrate this particular concept a bit. So let me use that particular tool. Just give me a second. You can just download this. I mean, you can easily go and download this particular tool. Right? You can click on download for free and you can get started. That's okay. All right. So this is how the tool normally it will look like. So you have a lot of devices on the left hand side. You can see if you click on on the left hand side is network devices. You get devices like routers, switches. Look into my cursors, so hubs, some wireless devices, security devices like firewalls, right? Some WAN emulation devices, etc. So you have end devices like PCs, you know servers, printers, IP phones, etc. Right? You can have devices like some sort of boards, actuators, sensors, right? Cable, different types of cable that you have might be serial cable, a console cable, a copper straight through, a copper crossover, fiber optics, IP phone cables, serial cables, octal cables, USB cables, etc. All right. So different types of emulator that you can get over here. So what I'm doing is right now is very simple. I'll select on end device. Let me take a couple of PCs over here on the main page, right? And what I can do is I can connect that. So normally two PCs when you connect, it will be of course a straight through, sorry, a crossover cable, right? So you will take a copper crossover. So select this icon and say copper crossover. Select that. Click on the PC, and you have got different types of ports that is available on this PC. So you'll select this Ethernet port, fast Ethernet port, which means it is offering you, 100 Mbps. So if it is only Ethernet, it means 10 Mbps. If it is fast Ethernet, it means it will offer you 100 Mbps. If it is gigabit Ethernet, it means it will offer you, 1 Gbps, and so and so, right? So it is, click on that FE port, that is basically your NIC adapter, and click on this PC again and plug it to this Ethernet port again over here, right? And then you can see the port labelings will appear. So it shows you that this PC is plugged to the other PC, and this is the interfaces that they're connected with. All right. So now what I can do is I can go to click on this particular PC, right? I can click on desktop over here, okay, and then I can click on IP configuration, and I can see that to a PC I can give either there are two ways to assign an IP address. I can go and assign an IP address statically to my PC, or I can go with something called as DHCP, that is Dynamic Host Configuration Protocol. So basically, I can have something called as the DHCP server by which my PC can get an IP address automatically. Okay, this is a different concept. So let me use static itself, where I'm assigning the IP address manually to my PC. So let me go and assign an IP address as, for example, 10.1.1.1. say the mask, when I click, it automatically knows that this IP will have a default mask of 255.0.0.0. You can change the mask values based on the requirement. That will be part of your subnetting class. So once I do subnetting, then you will understand, if I change it, what will happen. As of now, default gateway is not required. So default gateway is required if you're trying to reach to a different network. Okay. DNS server is also not required right now at this point of time. We're not going for an IPv6 configuration, right? It's not required. So just a normal IP and a mask you gave. That's it. Okay. Click on close. Okay. Click on close over here. All right. And then you can go to command prompt. Okay. There's this particular option. And if you want to expand, you can expand in that way. If you just type IP config, you can see what IP address this PC has. So this PC has got an IP of 10.1.1.1 and the mask is 255.0.0.0 that you're assigned right now. Okay. That's it. So if you go to another PC, click on that. The PC is powered on, so you can see it's powered on over here. Click on desktop, click on IP configuration and give the IP as 10.1.1.2. The mask is by default as this. I do not want any default gateway or DNS server for time being. Okay, keep it simple. Close, go to command prompt, type IP config. You can see that this PC has got an IP address of 10.1.1.2, which looks like that. If you want to see the MAC address, it is like IP config space /all. This will give the MAC address of the PC as well, right? So you can see this is the MAC address of the PC as D98B for PC number 2 over here. Okay, and for PC number this, if I go back again and if I type the command IP config space /all, I can see the MAC address as C3D4. Okay. If I want to see the local ARP cache, I can see with the command called as ARP space -A. So I'm on the first PC and I'm typing ARP space -A to see my local ARP cache. As of now, communication didn't happen, so it is not going to, locate to anything. So now what will happen is in the command prompt, if I try to ping, 10.1.1.2, you can see that I'm getting an echo reply from 10.1.1.2, right? It's a 32-byte, packet. This is your basically average time of your echo request to go and reply to come. That TTL stands for time to leave, right? Which I'll discuss later in CCNA classes and all. You will understand more about this TTL functionalities. But as of now, it's fine. Okay. So you can see that, the number of packets that you've sent is 4. You received 4 packets. There was no packet loss, etc., etc. Right. But sometimes what happens is when you ping for the very first time, it's a similar to environment, right? When you ping really for the very first time, so what happens is, if the destination MAC is not known, then the PC will do an ARP to find out the destination MAC. Okay, because of which the ICMP packet will be the first packet is lost. So generally, what I'm doing is I'm generating here 4 packets, right? And each and every ICMP packets has got a time limit of 2 seconds, right? So every packet is generated after every 2 seconds. So might be you generate the first packet, and within 2 seconds you have not got the ARP reply, so your first packet is lost. Okay, and the second packet you got the ARP reply, so from second packet your replies would be seen. So out of 4 packets, might be 1 packet was lost because ARP was not done by that time, and you got the reply of the remaining 3 packets. Right. So this thing can happen. So if I look again to ARP space -A, you can see that you found out the remote IP over here, and this is the remote MAC address that you've learned. Okay. All right. So your pings are successful over here, right? But if I actually change, this IP to something else, say I make it 20.1.1.1, something different IP. Okay, that's fine. And if I go to command prompt now and show you that the IP has been changed to a different network altogether. So if I see IP config, all right, the IP address has been changed to a different network altogether. So now if I try to ping, if I go to the first PC and try to ping, 21.1.1, that will not be happening at all, right? Because this PC does not know how to reach it, right? Does not know how to reach to a different network. Okay, so you get the replies as request timed out. All right. So let me go back and assign it back to your, the normal condition that it was. So say I revert it back to 10.1.1.2 with the mask. go back to command prompt, ipconfig, and it is back to 10.1.1.2 again. Okay, now from PC or from this PC only, let us say if I try to ping back to the PC one, so it is 10.1.1.1 over there. I can see I'm getting a reply. All good. All right. So okay, so you can see, I mean, you can also check with this particular, there is a data that you can see that I've taken this, data. Basically, this is this is an ICMP packet data. So if you don't want to go to your, in packet tracer, this is a beautiful thing that you can get. It's like not going to the command prompt and pinging to the destination PCs. You can select, ICMP traffic from here directly, click on this source, click on this destination, and you can see what is the status over here. It says, okay, the status is successful. It's an ICMP packet. The source was PC0, destination was PC1, and it was happening all good, right? Okay, so what is the basic stuff over there, right? So we'll actually use, you guys can use packet tracer to practice it, your routing, your basic switching, or this particular course itself. But I'll be using a couple of them. I'll be using EVANG to show you some routing and switching demonstrations, plus also packet tracer. So you have the gist of both the environment. So I mean, packet tracer is something I would recommend at this stage. It's more than enough for you guys to practice and to work with.